Look, if you are writing basic CRUD applications, you might never need to think about this. You spin up a thread, it dies, life is good. But the moment you step into the world of high performance servers, batch processing, or complex asynchronous workflows, the stakes change. The executor framework isn't just a fancy way to run runnable objects. It is a contract between you and the CPU about how work gets done. In this video, we are going to cover three massive pillars of knowledge: the life cycle, the three states of an executor, and how to transition between them smoothly without crashing your application; the scheduler, how to make Java do things while you are asleep, that is, delayed or periodic tasks; the pattern, how to stop writing dumb blocking code and start using Future, Callable, and the incredible powerful completion service to build applications that feel lightning fast even when they are waiting for the network. So grab a coffee. This is going to be a long ride, but I promise by the end you'll be writing concurrency code that will make your tech lead ask you who taught you that. Alright, let's break down the life cycle of an executor service. An executor service has three primary states: running, shutting down, and terminated. When you first create an executor, for example, via executors.newFixedThreadPool method, it is in the running state. In this state, it can accept new tasks and execute them. When you decide to shut down the executor, you have two options: graceful shutdown with shutdown method. Calling shutdown method initiates a graceful shutdown. The executor will stop accepting any new tasks. Any task submitted after this call will be rejected, usually by throwing a rejected execution exception. However, tasks that have been already submitted, including those waiting in the queue, are allowed to be completed normally. The executor remains in the shutting down state until all ongoing tasks finish. Second option is abrupt shutdown with shutdownNow method. This method attempts to stop all actively executing tasks by interrupting the threads if they are responsive to interruption, and it prevents waiting tasks from ever starting. It returns a list of tasks that were awaiting execution, that is, those tasks that never got a chance to run, and it returns the list of runables. After this call, executor moves into shutting down state, but it tries to halt things as quickly as possible. Regardless of which shutting down method you are using, the executor eventually reaches terminated state, but only after all the tasks have completed or been forcibly stopped. Until then, JVM may not exit cleanly because the executor's threads are still alive. So, how to check for termination? So, you can check whether the executor has terminated with isTerminated method, which returns true only after it has completely stopped. Often you need to wait for that to happen before proceeding. The method awaitTermination with timeout blocks until all tasks have completed after a shutdown request or the timeout occurs or the current thread is interrupted. It returns true if the executor terminated and false if the timeout elapsed. A common, robust way to shut down an executor is to first call shutdown method, then wait for a reasonable time with await termination method. If the task don't finish within that time, you fall back to shutdown now method and wait again. This pattern gives your task a chance to finish gracefully, but also ensures that the application doesn't hang there indefinitely. And here is the implementation, a smart way to shut down. So in this code, first we try a graceful shutdown, so no new tasks accepted. We wait here for existing tasks to finish, but not forever. If 30 seconds pass and it's still not terminated, we force it. We wait for a bit for the forced shutdown, else we log a warning that executor did not terminated. If the waiting thread itself is interrupted, we propagate the interrupt and also try to shut down immediately. This two-phase approach is a safe and practical way to manage executor lifecycles in production system. It ensures that resources are freed and the application can exit cleanly. But here is the thing. Lifecycle management is just a boring admin work. That's the stuff that prevents crashes. But what about the stuff that wows users? What if you need something to happen not now but later? Most developers throw their hands up and use thread.sleep in a loop. Don't be most developers because the executor framework has a secret weapon for handling time itself. Let, let's talk about scheduling. If you ever need to run a task every 5 minutes or send a keep alive ping after 10 seconds of inactivity, your first instinct might be Java util timer. Stop right there. Timer has issues. If one task throws an exception, the whole timer dies. It also doesn't play well with multiple threads. Instead, we have scheduled thread pool executor. It's like a normal executor but with calendar. This is how we can create scheduled thread pool executor. We can run task once after 10 seconds of delay, or we can run the task every 2 seconds after initial 5 seconds of delay. We have already gone through the constructor parameters and scheduler methods in previous video. I would highly recommend you to watch that. Now in this video, we will understand how does this scheduling actually work under the hood. It uses something called as DelayQueue. Imagine a DelayQueue as a special conveyor belt. You put an object on it, but you tell the belt this box cannot be picked up for 10 seconds. The belt sorts the box by the timer they expire. The box that needs to be picked up the soonest is always at the front. The scheduled thread pool executor has a worker thread that just does this. Look at the front of the delay queue. If the task's delay has expired, take it, run it. If task is recurring, calculate the next delay and put it back on the build. If you ever need to build your own scheduler, maybe for a job queue, you don't need to reinvent the wheel. Just use DelayQueue wrapped with a thread pool. It's one of the most underrated classes in Java. As you can see here in a lead code discuss section, tech giants like Uber, LinkedIn, Rubrik frequently ask candidates to design scheduled thread pool executor because it is an all-in-one test of senior level engineering skills. Unlike a standard algorithmic problem, this question evaluates your ability to build a complex production ready system that handles real world constraints. So let's try to build our own custom scheduled thread pool executor. This is our custom scheduler that mimics scheduled thread pool executor from Executor framework. A delay queue is a backbone of scheduling. It holds tasks ordered by their delay. Tasks only come out when their time has arrived. We use an executor service to manage worker threads. These threads will continuously pool the delay queue and execute tasks. So here's how we construct the object. We initialize a fixed size thread pool. We pass a thread factory with each thread has a name scheduler worker. An atomic integer ensures unique thread name safely in concurrent environment. We start the worker threads and for each worker we submit dispatch loop. So let's see what this dispatch loop does. This loop continuously pulls tasks from delay queue and executes them. This loop runs forever until thread is interrupted. DelayQueue.take method blocks until a task's delay has arrived. Once task is ready, it is executed. If task is periodic, we reschedule it by updating its next trigger time and putting it back into the queue. Now here we have these three famous methods from schedule executor service. First is schedule method, a one-time task after a given delay. So we create a scheduled task with one-time delay and put it in delay queue. Next is schedule at fixed rate, scheduling a repeating task at a fixed rate. First run after initial delay, then every period. So again, we create a scheduled task by providing initial delay and the fixed interval and put it on a delay queue. The third is schedule with fixed delay, which, which waits until task finishes. Once task finished, it then applies the delay before starting the next run. Notice here we take the period but we are inverting the sign. This is to distinguish between fixed rate and fixed delay task. At the end, this is how we shut down our executor. Stops all worker threads immediately, ensures no further tasks are executed. And here we have the most important static inner class, which represents scheduled task. It implements both runnable, so it can run, and delayed, so it can stay inside DelayQueue interfaces. Here we store the task, its period. If period is greater than 0, that means it's fixed rate task. If it is less than 0, then that means it's fixed delay task. If it is equal to 0, that means it's not periodic. And trigger time, the next execution time in nanoseconds. So our first constructor is one-time task, runs after initial delay. The second task is a periodic task, which has initial delay and the period. The trigger time is calculated as the current time plus the delay. The gate delay method from delayed interface tells the queue how much time remains before the task is ready. So we subtract the next trigger time with the current time. Compare to method ensures tasks are ordered by their delay. So we compare the delay between two tasks. The run method actually executes the task. Each periodic method checks if the task is repetitive. And here is the rescheduling logic, which updates the next trigger time for periodic task. Before going to the logic, let's understand fixed rate tasks and fixed delay task. So fixed rate task, let's say if it starts at 9 with 10 minutes of initial delay, the first run at 9.10 and then subsequent runs will happen at 9:20, 9:30 and 9:40. For fixed delay, if the first run happens at 9:10 after 10 minutes of initial delay and first run takes 9.30, the next run will happen after 10 minutes, that means at 9:40. So this is how fixed rate and fixed delay tasks work. So let's come back to the rescheduling logic. So if period is greater than 0, that means the task is fixed rate task. So the next run is previous trigger time plus the given period. And if period is less than 0, that means the task is fixed delay task. Then the next run will happen the current execution time plus the given delay. Here we are subtracting the period because for the fixed delay we are taking period as negative. And this is how we can use this custom schedule executor. We create a scheduler with two worker threads. This is how we can run one-time task which runs after 2 seconds, fixed rate task which runs every 3 seconds after initial delay of 1 second, and this is how we run fixed delay task which waits for 2 seconds after completion before next run. I have intentionally put main thread on sleep for 12 seconds so that you can see this happening in the logs, and then we shut it down. Let me run this code. So you can see our fixed delay task started, then another thread picked fixed rate task, then we got one time task got executed, then fixed delay, then fixed rate. And this is how the execution happened. And after 12 seconds of sleep, the main thread shut down the scheduler. Try running this code yourself. You will see that the two worker threads process these periodic or delayed tasks and the queue handles the overflow. It's a great way to really understand what's going on. So we know how to manage the server, the life cycle, and how to manage time, that is scheduling. But the biggest mistake I see senior devs do, they treat all tasks the same. They have big monolithic tasks like rendering a web page and they run it on one thread. They leave performance on the table. It's time to talk about exploitable parallelism. Let's switch gears. Imagine you're building a backend for a massive online store like Java Mart. Every night you need to process thousands of invoices, and for each invoice, you have to do three things. First, fetch the customer's loyalty discount from the CRM, which is a database call. Calculate the final price, including taxes, which is a CPU work. Generate a PDF invoice, which is again an IO writing to a disk. The most straightforward way to write this is sequential invoice processor. So we loop through all the invoices, we fetch the discount from the CRMDB, we calculate the price and we generate the PDF. What's the disaster here? For every single invoice, we are sitting around waiting for the CRM to respond. The CPU is bored, the disk is idle. Meanwhile, the finance team is waiting for those PDFs so they can get paid. This is a crime against business velocity. The user, in this case, the finance manager, stares at the processing screen for hours. If one CRM call is slow, the whole batch grinds to a halt. So, what do? We need to send out multiple CRM requests at once. We need receipts so we can collect the results later without blocking the main loop. And here enters callable and future. Callable is a perfect option here because fetching a discount returns a big decimal value and it can throw an exception if the CRM is down. So we create a one big task to fetch all the invoices and we submit that task to get the future. This is better, right? We parallelized the CRM calls against the nothing. The main thread literally has nothing to do while waiting for that one future. We just moved the bottleneck from a sequential loop to a background thread, but it's still a sequential loop inside that thread. If fetching discounts from 1000 customers takes 10 seconds, this processor still takes 10 seconds, similar to the previous one. We haven't gained any real throughput. We just hit the waiting from the main thread, which is useless because we can't proceed without the discount anyway. This is the same trap as before. heterogeneous tasks are hard to parallelize when they have dependencies. We have to rethink the task boundaries. So, what's the best way? The pro way is using the completion service. What if we treat each invoice as an independent unit of work? Each invoice needs its discount fetched, its price calculated, and its PDF generated, all in one task. If we submit 1000 separate tasks to a thread pool, we can process up to 10 invoices concurrently. But then we have the same problem as before. How do we know which invoice finished first? We don't want to wait for invoice number 1 if invoice number 5 finished earlier and it's ready to be archived. We need a system that yells, "Hey, invoice number 5 is done, take it," and that mechanism is the completion service. So we submit each invoice as its own task to a completion service. Now, instead of waiting for all, we grab the result as they complete. The completion service dot take method blocks until the next invoice is fully processed. But the future dot get method doesn't block because the result is already ready. This is the magic. The finance manager sees the invoices appearing on the dashboard as soon as they are ready, not in some arbitrary order. If one CRM call is slow, it doesn't hold up the others. This is how real world batch processing engine works. This is how you build systems that scale. Let's take this to the next level. Imagine you're building the backend for a travel site. A user searches for a flight to Tokyo. You need to send a request for price estimates to Air India, Japan Airlines, or 10 other airlines. You can't wait for the slowest airline. If one server is down, you can't make the user wait for 30 seconds. You have a time budget, maybe 2 seconds. How do you do this? You could use a loop with completion service, but there is an even cleaner way, which is invoke all method with timeout. So here is our code task to fetch a quote for one company. It implements Callable. Unlike Runnable, Callable can return a value. Here in our case, it's travel quote, and it can also throw exceptions. It makes a network call and returns the result. So here is our code retrieval method within given budget. So it takes set of travel companies, travel info, and timeout, and returns the list of travel code. So we first build list of code tasks, one for each company. And here is the magic line. We submit all tasks at once to executor service. If tasks don't finish within given time, they are cancelled. Once this is done, we loop through the futures. If the task is finished within the time, the get method returns immediately. If the task was cancelled due to timeout, the get throws cancellation exception. So we add a placeholder, maybe timed out or failed accordingly. The invoke all method is a beast. You hand it a collection of tasks and a timeout. It submits them all and then it blocks until one of three things happens. All tasks finish, the timeout expires, the calling thread is interrupted. If the timeout expires, it automatically cancels all the unfinished tasks. You get a list of futures back. Some are done, some are cancelled. You handle them accordingly and return a result to the users within your 2-second time budget. This is resiliency. This is professional grade code. Alright, let's land the plane. We have covered a ton of ground today. We started with the life cycle. We learned that shutting down an executor isn't just a method call, it's a state machine. Shutdown method for a polite goodbye, shutdown now method for a firm alarm, and await termination method to wait for the dust to settle. We then spent time with scheduled executors and picked under the hood at the DelayQueue, the hidden gem for building time based systems. And finally, we transformed a slow, clunky invoices processor into a responsive powerhouse by moving from runnable to callable and then unlocking true parallelism with the completion service. We even simulated a high load travel portal using invoke all method to prove we can handle failures without ruining the user experience. One last thing to remember, don't just throw threads at a problem, design your tasks appropriately. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.